All right, so hello everyone. Thank you for joining us today. Welcome to our presentation of Tinker. It's a project we are all incredibly proud of. We've spent the last few months working on it, and we couldn't be more excited to share it with you today. So thank you for coming. Let's meet the team. First off, I'm Jared Naylor, and I'm here with my teammates Sugihara and Peter Hua. We are a team across 2 time zones. Sho and Peter are both from the Pacific Northwest. Peter from Vancouver and Sho from Seattle, while I am from the flatlands of West Texas. A little pre-presentation hype for the team here. Sho is an absolute surgeon when it comes to recognizing a problem and then solving it. And if there was one word to describe Peter, it would be precise. As for myself, I'm an excellent hype man. Let's talk Tinker. So first, what is Tinker? Tinker is an open source, self-hosted backend-as-a-service, or BaaS, that accelerates development speed through automated configuration, deployment, and an intuitive table editor. We'll get into how Tinker is able to do all this a bit later on, but the question for the moment is, who is Tinker for? Tinker is for the developers that want to avoid all of this. These are just a few of the installation and configuration challenges required to set up a backend server and its database. For developers with a fresh idea for a proof of concept, that initial enthusiasm could be worn down one configuration at a time. Tinker is for a developer looking to move quickly from idea to proof of concept. When building from idea to proof of concept, the development of a web application may be slowed by technical challenges unrelated to the core concept. All right, now that we've covered what Tinker is and who it's for, we'll next examine the deployment and configuration challenges that a software developer faces, and some services to offload some of those concerns. Then we'll examine how Tinker tackles some of those challenges and how it fits into the broader landscape of existing solutions. We'll also take a look at the components that make up Tinker's architecture, the decisions that drove us there, and the challenges we faced during its development. First, we'll start at the very beginning, the basic 3-tier architecture. The traditional architecture for web applications consists of a front-end, back-end, and a database. The front-end facilitates interactions between the client and the application back-end. The back-end receives and processes requests from the front-end, then issues appropriate responses. And depending on the request, the back-end may interact with the database to manage data storage or retrieval. As most of you are aware, development often begins from the local machine. Once the developer believes the application is production ready, the application must be deployed. Even for a simple application, this process involves setting up a web server and possibly database, which involves various technical configurations, dependencies, and settings. Developers may find this process time-consuming or challenging if they are unfamiliar with the technologies used. When the application is ready for deployment, developers have options on how to deploy the backend to a server. One approach is to use on-premise, where server equipment and space is managed by the company itself. Another approach is to choose an infrastructure as a service, which abstracts away the physical management of the server. However, what the user gains in convenience through the abstraction, they lose in control over their infrastructure. And that brings us to Tinker's domain, backend as a service, or a BaaS. Similar to infrastructure as a service, BaaS abstracts away the configuration of the backend server. It abstracts away configuration complexities such as managing databases, web servers, application servers, virtual machines, and containers necessary to keep an application running. Once again, the abstraction does come with a trade-off: reduced control and flexibility over the backend architecture. So why choose a BaaS? Well, configuring a backend server remains challenging and time-consuming. As we hinted earlier, a litany of configuration steps need to be completed. For developers who lack the expertise or desire to handle server-side infrastructure, BaaS allows developers to shift their focus toward front-end development. Another benefit is, in RESTful web applications, API endpoints responsible for handling common CRUD operations can be automatically generated. The developer no longer has to create boilerplate data endpoints for their front end to issue requests to. For these reasons, BaaS services are popular to get front-end heavy applications deployed quickly. If a developer goes in the direction of using a BaaS, an important consideration in deciding which service to use is what type of database the application will use and whether the BaaS supports it. Databases roughly fall within two categories: relational and non-relational. Relational databases share a common core, restrictive schemas, and utilizing SQL for querying. The developer defines the structure of the data through the schema and by applying constraints to the table's columns. This structure enables complex queries, such as joins. On the other hand, NoSQL is a broad term that covers databases that are schema-less, which makes it easier to evolve the data model over time and offers more flexibility to store data in different ways. For these reasons, NoSQL may be attractive to an early-stage application where the data's final structure is yet undetermined. However, using a NoSQL database may present challenges as the application evolves. One challenge is that NoSQL databases have diverse approaches, particularly regarding schema handling, which ranges from schema-less to even mimicking a relational database. SQL, on the other hand, adheres to international standards. Developers already versed in SQL would need to learn a new query language or database-specific syntax. When prototyping, SQL backend-as-a-service users have one less concern to address. A prototype can be developed quickly using a NoSQL BaaS, but what are the eventual consequences of this design decision? One consequence of choosing a NoSQL database is the difficulty in modeling relationships between entities. Data often relates to other data, and if an application's data is highly relational, this could push more business logic to the front end. In a SQL database, foreign keys establish relationships between tables. Combining data through joins can be left to the database engine. Lastly, SQL databases are universally ACID compliant, but the same cannot be said for NoSQL. Data inconsistency and data duplication can become an issue for a prototype using NoSQL as it matures. When selecting a NoSQL database for short-term gains, one should consider the long-term implications that may arise once the application matures. In many cases, a relational database is considered as the default choice. For these reasons, we decided Tinker should use a relational database. However, most BaaS solutions use a NoSQL database due to the flexibility and data storage that NoSQL allows. Companies like AWS and Google offer BaaS solutions such as AWS Amplify and Google Firebase with proprietary NoSQL databases. For those looking for an open source solution that uses a relational database, there's Supabase. Tinker's use case of rapid prototyping with structured data most aligns with the capabilities of Supabase. A unique aspect of Supabase is that it simplifies using a relational database through a user interface. Through the UI, users can perform common database operations, such as creating tables and adding rows. This allows a user to make schema modifications as their application evolves. In addition to the abstraction of writing SQL queries, Supabase also automates backend configuration. Supabase does, however, host user projects by default, which may be an issue for some users looking for more control. Supabase offers the option to self-host, but the user would need to deploy the individual open source components that make up Supabase on dedicated servers in the cloud. In this scenario, the user avoids the installation and configuration of backends, but now must deal with the installation and configuration of the self-hosted BaaS. Here's a diagram of a few BaaS services and Tinker in comparison. Although Supabase was the inspiration for Tinker, we sought to develop a framework that could mimic their user-friendly dashboard while also streamlining self-hosting on virtual private servers in the cloud to give our users more control. I'll now pass it off to Sho to talk about Tinker's architecture.
Thank you, Jared. As introduced, my name is Sho, and I'll be walking you all through Tinker's architecture and the puzzle pieces that make Tinker possible. First off, as a high-level overview of what Tinker is architecturally. Tinker is comprised of two user-facing components, the command line interface, the CLI, and the dashboard UI. The CLI is responsible for automated AWS resource provisioning for users to self-host Tinker's admin backend and any needed backend servers for their front-end applications, all within their AWS environment. On the other hand, the dashboard UI is a browser-based interface that empowers users to manage each server's database using an intuitive table editor. All right, let's look at the dashboard UI and the table editor. The dashboard allows users to manage all of their backend databases. After selecting a backend, users can manage their database using the table editor shown here. This table editor is the heart of Tinker's dashboard UI. It allows a user to create, edit, delete tables, insert, edit, and delete rows or data. It also allows users to set constraints such as primary keys, foreign keys, not null, and unique. This table editor allows working with a PostgreSQL database extremely easy because it allows a user to create the entire schema of their database without having to write a single SQL statement. And for someone not familiar with SQL statements and SQL syntax, this table editor can be very helpful for speeding up the development of front-end applications. Tinker's command line interface was published as an NPM package for easy download and use. It is responsible for handling all AWS resource provisioning that make up Tinker's self-hosted infrastructure. Through the deploy and create commands, users can deploy the Tinker's admin backend and use your backend servers. It handles deletion of those resources when no longer needed through the delete and destroy commands. Tinker was made possible through the myriad of options and components that AWS offered. AWS offered the automation tools and cloud infrastructure we needed for Tinker to offer a seamless self-hosted backend as a service. Some of those core components we used were EC2 instances for both Tinker's backend server and any servers the user may need for their front-end applications, CloudFormation for all of our automation, and an application load balancer for handling traffic to the EC2 instances. CloudFormation is the heart of Tinker's automated self-hosted infrastructure. Tinker's CLI uses CloudFormation to set up and deploy Tinker's infrastructure within a user's AWS environment. CloudFormation handles the entire deployment and provisioning process of Tinker's dashboard UI, EC2 instances, load balancer configuration, and domain name management. All of this is made possible through customized CloudFormation templates, which are sent to CloudFormation whenever a CLI command is executed, such as deploy, create, or delete. Now that we have a high-level understanding of Tinker's architecture, next we'd like to talk about the journey and the challenges we faced that ultimately led to the architecture we just explored. So first off, during Tinker's development, we needed an API layer to handle communication to the PostgreSQL data layer. We needed this API to handle requests from both the dashboard UI and users' front-end applications. A requirement for this API layer was that it needed to dynamically generate API endpoints unique to its respective database. For example, if our admin database had a table for projects, then the API would have to have an endpoint that allowed us to execute CRUD operations on our projects table. If a user's database had a table for movies, then the same thing. They would need an API endpoint that allowed them to execute CRUD operations on their movies table. Both of these API endpoints needed to be generated dynamically by the API and not hard-coded. To fulfill these requirements, we chose to use Postgres, an open source web server that automatically generates a RESTful API from a PostgreSQL database schema. By inspecting the database, it creates HTTP endpoints that allow applications to interact with database resources using standard HTTP methods and RESTful conventions. Postgres also handles tasks like request routing, filtering, sorting, pagination, and access control. We considered building the API layer from scratch using a web server framework such as Express and writing logic to dynamically create routes and endpoints. However, it made more sense to adopt an existing open source solution. Why reinvent a really good free wheel? For a user application trying to use Postgres, these endpoints might look something like this. An application might try to connect to the people endpoint, which connects to the people table within the database, and perform queries on that table using query parameters. These query parameters are what gives an application the ability to sort, filter, paginate, or join data within the table at each endpoint. Postgres also supports HTTP methods. These HTTP methods allow a user greater versatility when managing their data. These HTTP methods give a user CRUD operations on their data when connecting to their database through the Postgres API. Although Postgres solved many of our API needs and became an integral part of Tinker, it lacked the same level of flexibility that a custom solution would have offered. In subsequent sections, we'll explore the challenges that arose from choosing Postgres. So you can imagine that when we went to build our dashboard UI and table editor, Postgres automatically generated endpoints would prove extremely effective. Sending requests such as selecting, inserting, editing, and deleting rows or data through the table editor became very straightforward and simple. However, Postgres had a few limitations. First, it did not have endpoints for data definition language, such as creating, editing, and deleting tables, which was absolutely crucial for making a functional table editor. Second, there was no way for us to add custom endpoints to Postgres, which could have circumvented the first problem. So to address these issues, we turned to PostgreSQL's stored procedures and Postgres remote procedure call, or RPC API endpoint. So what are PostgreSQL's stored procedures? Stored procedures are functions within a relational database that can store and execute SQL statements. They accept arguments and can return a value. PostgreSQL's stored procedures were absolutely amazing, as they allowed us to keep all SQL statements and logic within the SQL database and outside of the front-end code. These stored procedures allowed us to create all the necessary SQL statements for creating a functioning table editor. Some of those stored procedures included creating tables, editing table names, editing individual columns within those tables, and deleting tables. The example shown here is us storing a create table function, which takes 4 arguments, creates a new table, then returns true when the new table is successfully created. So now that we know what stored procedures are, what are remote procedure calls, or RPCs? RPCs are a mechanism that allow a computer program to execute code or procedures on a remote server as if they were local functions or procedures. In other words, RPCs enables communication between different systems, allowing them to invoke functions or methods in a distributed manner. RPCs are great because they facilitate code reusability, resource sharing, and scalability. In this example, the client is sending a request to the server to invoke the function foo. The server receives this request and executes the function foo and passes in the given argument. The server then returns the result of the function foo back to the client. So what would this look like for Tinker? In Tinker's case, the dashboard sends a request to Postgres RPC endpoint, specifying the stored procedure we want to invoke. In this case, create table. Postgres dynamically generates RPC endpoints for all stored procedures within its respective PostgreSQL database. In this diagram, we want to create a new table and send the required arguments. Postgres takes the required arguments and sends the request to PostgreSQL to invoke the stored procedure create table. PostgreSQL takes the given arguments and executes the stored procedure. It then sends the results back to Postgres. Then Postgres returns those results back to the dashboard. The dashboard takes those results and updates the UI. From this, you can imagine that when combined, SQL stored procedures and Postgres RPC endpoint open the door to endless versatility. And that versatility gave us the needed solution for executing SQL statements not possible with Postgres other endpoints. As the title might suggest, Postgres' lack of custom endpoints presented us with another problem. We weren't able to use Postgres as a means of communicating to AWS CloudFormation. This is relevant because initially we wanted the dashboard UI to handle the provisioning and deletions of user backend servers. So we now had to figure out how we were going to provision and delete backend servers with CloudFormation. These are the options we considered to circumvent Postgres limitations. We could have coded logic into the front end that would allow it to communicate to CloudFormation directly, but that would require Tinker's dashboard to handle a user's AWS credentials. And we wanted to minimize the risks associated with sending a user's credentials over the network, so that option was out. We already had a working API, so creating a custom API server just for this problem seemed counterintuitive, so that was out. We could have provisioned a serverless function using AWS Lambdas, but this also required sending users credentials over the network, so that was out as well, which left us with option 4, expanding Tinker's CLI. If we look at this diagram that shows how Tinker is initially deployed, we can see that in order to communicate with CloudFormation, we need a user's AWS credentials, and those credentials are handled by AWS's CLI. When installing and configuring the AWS CLI, a user enters their credentials, and those credentials are stored in a config file. It is from this config file that credentials are pulled from when we deploy Tinker through CloudFormation. Tinker never handles the user credentials directly, and we wanted to keep it that way for security purposes. So expanding the CLI to handle other AWS provisioning seemed the logical choice. So we can see here that after expanding the CLI, it now handles all AWS provisioning and deletions. The user credentials are still only handled by AWS components. This worked out great for 2 reasons. First, by clearly separating the responsibilities of the CLI and the dashboard UI, we were able to consolidate all AWS provisioning related code and CloudFormation templates into the CLI and keep the front-end code free from any resource provisioning logic. Second, we avoided potential security concerns when embedding a user's AWS credentials within Tinker. We took the security of a user's AWS credentials very seriously and wanted to avoid handling them within any part of Tinker. However, despite the added benefits of expanding the CLI's functionality, there was a trade-off. The dashboard would now no longer be able to manage user backend provisioning and would now be strictly limited to data manipulation and definition. This made the dashboard UI less intuitive, as users would now be required to create and delete backend servers through their terminal. Peter will now take it from here and continue with our next puzzle piece.
Thank you, Sho. A challenge we faced while developing Tinker was database security. Since users' PostgreSQL database and Postgres API are public-facing, that raised concerns for us due to their lack of default security measures. To overcome the security concern, we leveraged JSON Web Tokens for authentication and PostgreSQL roles for authorization. Authentication establishes the user's identity or who they are, while authorization checks whether that user has permission for their request. PostgreSQL uses roles to manage privileges. They allow administrators to define permissions assigned to roles. By doing so, permissions control what a role can perform. In this example, a read-only role has permission to read tables, but does not have permission to create tables, insert data, or delete data. JSON Web Tokens are used to transmit secure information as a JSON object for authentication. They consist of 3 parts separated by periods: a header, a payload, and a signature. The header contains the token's type and cryptographic algorithm used for its signature. The payload contains information about the user. The signature is created by encoding the header, payload, and a secret key with the cryptographic algorithm. Postgres verifies the signature to determine the token's authenticity. When a request is made to Postgres, it decodes the JSON Web Token using its configured secret. If the JSON Web Token is valid, Postgres assumes the claim role in PostgreSQL. If the claim role in the JSON Web Token does not exist in PostgreSQL, or if the secret used to encrypt the JSON Web Token does not match Postgres' secret, the authentication process fails and the request is rejected. When connecting to Postgres without a JSON Web Token, Postgres will connect the user to PostgreSQL's anonymous role, which has predefined limited privileges. In Tinker's case, the anonymous role is only privileged to handle user logins. When logging in, the user provides their credentials. Without a JSON Web Token in the request, Postgres assumes the anonymous role. The anonymous role has permission to check the provided credentials with the stored credentials. If they match, the login is successful. Another challenge that we faced was implementing HTTPS for Tinker. As part of the initial Tinker deployment, the user inputs the region information and the domain they want to use. During deployment, a randomly generated JSON Web Token secret is created. Postgres servers are configured to use this secret to decode JSON Web Tokens from incoming requests. Additionally, the secret is displayed as an output for the user. Users include the secret in the sign-up form when creating a new account. The user only needs the secret for sign-up, but won't need it later for login. When submitting the sign-up form, the front end generates a JSON Web Token using the provided secret and includes in it the sign-up request to the backend. Upon receiving the sign-up request, Postgres decodes the JSON Web Token and stores the new user's credentials in the admin database. Now, users can sign in from different clients without needing the secret. Whenever a user signs in, Postgres verifies the provided credentials with the stored credentials in the admin database. Upon successful login, PostgreSQL mints a JSON Web Token containing the admin role. Future requests to Postgres include this JSON Web Token, which authenticates them as admin users and authorizes them to interact with PostgreSQL databases. An issue we identified with the sign-up flow design is that Postgres does not implement HTTPS. That meant that JSON Web Tokens and user credentials in requests are exposed to potentially malicious actors. JSON Web Tokens are encoded, not encrypted. This means that the JSON data can be seen by anyone intercepting the requests. We needed something upstream of Postgres to handle HTTPS traffic. We chose to use an application load balancer, or ALB, responsible for handling all HTTPS requests to Tinker components and routing HTTP downstream. To establish an HTTPS connection, a TLS handshake first takes place. During this process, the server sends its TLS certificate to the client. The client then verifies the authenticity of the certificate. Another approach was to create a certificate for each user backend. Ultimately, this is more complex than centralizing the TLS certificate in the application load balancer. Another challenge we faced was how to handle migration when a user is looking to migrate off of Tinker. Although there are many benefits to using a backend as a service, there is a looming possibility that the BaaS chosen will end their services. Or the user may need to customize their backend, such as setting data retention policies or choosing geographically where data is stored. For example, needing to comply with data sovereignty laws, which requires storing data in a specific location. But that location may not be supported by the managed backend as a service, which requires user to migrate their application. And these are reasons why we chose Tinker's infrastructure to be self-hosted in a user's AWS environment. However, even for a self-hosted solution like Tinker, we recognize there are still reasons why a user may want to eventually migrate off Tinker. For example, if a user wants to migrate from AWS to a different cloud service or switch to an on-premise servers, we wanted to minimize that pain. In cases like these, PostgreSQL's pg-dump command can back up data and schema. These files can then be used to recreate the user's database during migration in a new environment. The final challenge we faced was automating deployment. During the initial deployment of the admin backend and for user backend deployments, Nginx, Postgres, and PostgreSQL must be installed and configured. This is done using CloudFormation templates, which define the AWS resources that get deployed and also the configuration of them. This means that templates include Linux commands to install, configure, and run Nginx, Postgres, and PostgreSQL. The problem that we ran into through this approach was that the CloudFormation templates included a long list of Linux commands that were difficult to understand. As the template grew, its maintenance became increasingly cumbersome. To streamline the deployment process, we utilized Docker. Docker can package applications and their dependencies into isolated containers. These containers can be deployed and run consistently across any underlying Linux-based host. In short, it simplifies the process of installing and configuring applications. We leverage Docker to run Nginx, Postgres, and PostgreSQL in containers. Since Docker containers are isolated and Postgres needs to communicate with PostgreSQL, we use Docker Compose to create a network that connects them. Within a Docker Compose template, services are defined for Nginx, Postgres, and PostgreSQL. By adopting Docker, we simplified our CloudFormation templates. Rather than cluttering the templates with numerous installation and configuration commands, Docker containers encapsulate all these steps. This extracted the logic from the CloudFormation template and placed it in an organized location, the Docker Compose template. Docker added an additional layer of complexity, which impacted both our development of Tinker and its users. Users seeking to fine-tune their PostgreSQL configuration now have to understand Docker and Docker Compose. For example, changing settings such as setting how much memory PostgreSQL uses, the cache size, the maximum concurrent database connections, what database activities are logged, and where to store it. These tasks are now less user-friendly, since users are now required to go into a container's command line, which increases the complexity of the process. Although we achieved our objectives for Tinker, we identified opportunities for future improvements. There were two features we were interested in developing. One, we'd like to incorporate an SQL editor directly into the dashboard UI. This feature would give the user full SQL functionality. Second, we'd like the ability to import data from a CSV file and also export data to a CSV file. Additionally, we'd like to provide a user-friendly database dump through the dashboard UI. And that concludes our presentation. Thank you for taking the time to hear about Tinker's journey. We'll now answer any questions you have, and Jared will moderate that discussion.
Yep. Long-time listener, first-time caller. Just push your questions to the chat or the Q&A, and we'll do our best to get them answered for you. What was your favorite part of working on Tinker? I guess I could take that one. I mean, we can kind of go around the horn here. I really enjoyed building out the dashboard. I think that was really interesting. I think like tackling like infrastructure concerns, you know, kind of for the first time for a project of this size was really interesting too. So between those two things, but I'm definitely leaning towards the dashboard just because you get the visual payoff once it's complete. What do you think, Sho?
I think one of the most satisfying moments was when the dashboard connected to the backend and all the automation worked and the HTTPS worked and everything was working the way it was supposed to. And just that moment was like a hallelujah moment. So I think one of the greatest, I think one of my favorite parts of working on Tinker and as a group was the camaraderie that was involved, and then the satisfaction that came once everything was finished. I really enjoyed working on the front end part. Majority of my work was on the front end, and I really enjoyed that as well. But I think for the most part, the most enjoyable part was working as a team, and then just having that finished product, that satisfaction of we made this, it works, it's awesome. So yeah.
That's a great answer. I'd like to add camaraderie to my answer. All right, so I'm adding that. Peter, what do you think?
Yeah, I mean, I don't want to repeat what Sho just said, but I really enjoyed working with like a really excellent team. I really enjoyed, you know, working on a project that was difficult, but with team members that were really highly motivated and all share a very high level of technical competence. So I would say like the coding part wasn't so much the challenge and wasn't really more of like the interesting discussions we had. I think a lot of the interesting discussions we had were like, you know, evaluating different choices and considering the trade-offs. So yeah, I really had fun working as a team.
Awesome. Another excellent answer. Okay, so we do have one in the Q&A chat here. So this is sort of posed to all of us because it's not too specific to the project. I think it's just more about like the development of it. Did you find any particular AI tools useful in researching / building a project of this complexity? And great job, you guys. Looks awesome. Thanks, Josh.
I guess.
I think.
Oh,
yeah.
Sorry. Go ahead.
No, Peter, go ahead.
Oh, yeah. I was gonna say I think that yeah, there's been definitely you know, a lot of buzz around AI in the past year, and we're definitely not strangers to using AI tools. So like ChatGPT, I think is an excellent resource when it comes to doing research or making some like boilerplate code to understand something. But I think it does have to be like a nuanced take on that, because a lot of times, you know, you might ask questions to an AI, but the answers you get may be not entirely correct, or sometimes it's just flat out wrong. So I think it can be definitely leveraged to do research as a tool for your coding, but it definitely needs to be taken with a grain of salt sometimes. So I would use it as like one tool in my tool belt, but not exactly something I would rely on to build out, you know, the entire application, so to speak.
For sure. Yeah, you got to see it through the critical lens, because sometimes you can just take one look at the response. It's not even close to what you were looking for. But you know, sometimes it's incredibly valuable. So that's a good answer there. Okay, we've got another one here. This is about working with the AWS components. So Peter, I think this might be for you. What was it like to learn and implement AWS components for your project?
Yeah, sure. I would say that, you know, AWS was definitely like a very daunting thing for us at the start of this project, because we had high-level understandings of what some of the components were, but really to build something of this scale using AWS, we felt a little bit nervous for sure, because there are so many AWS products, and the documentation is quite difficult to parse. So our learning process for that was to read as much documentation as we could, leveraging things like Stack Overflow, watching tutorials and videos. And I think having the hands-on practical aspect of this project, having to, play around with AWS, try things, that really helped to solidify the theoretical knowledge you get from reading documentation, because ultimately, you can read as much documentation as you want, but I think the real learning there was just kind of playing around, tinkering, seeing what works, seeing what doesn't. And so that was kind of our learning process for AWS.
Tinkering, nice plug. Nice plug there. Yeah, any other questions? Push them to the chat or the Q&A. Okay, here we go. So how did you come across this project idea? I think we can pose that one to the group here.
I can
yeah, show hit it.
So the beginning of our research phase for a project idea, we were in like all over the place. We were all over the place. And then Peter found Supabase, which was the idea behind Tinker. And I fell in love with Supabase. I really enjoyed working with PostgreSQL backend core with Ruby. But one caveat I had with that was like I really hated working with SQL through the terminal. Like it was a really big pain, and the look was horrible. And when Peter told me about Supabase, I absolutely fell in love with the table editor. And for me, that was the biggest pulls of being able to look at data, relational database with the table editor, and then being able to alter and manage that data through the table editor was absolutely mind-blowing to me. And then from that, we expanded into looking into backend as a service. But I think Supabase and their product and their take on how to manage data and relational data, I think was a really big pull. At least in my mind, it was. And so we just rolled with that.
For sure. Yeah, I'd agree with you there, Sho. It's like when Peter first introduced us to Supabase, it was just sort of undeniable for all of us, because we had spent so much time in like the SQL course or, like early on in like the building out a web application. So we were very familiar with like working from the command line, and to see everything just streamlined in like a really nice looking dashboard UI. And then the fact that you could manage your own projects, it was such like a natural direction for us to take. Yeah, looks like we got another one here in the chat. So this one could be posed to the group again. So what were some of the most difficult design decisions? I'm sorry. Okay, so what were some of the most difficult design decisions?
I think one that comes to mind for sure is deciding how to provision the user backends. So our initial vision for that was to do that from the dashboard, and that was something that I think Supabase also does. So there's like there's a button you can click to spin up a backend, and we felt like that was very user friendly, very user intuitive, and while definitely possible, we've ultimately found that there was a lot of caveats to that particular design choice. So we looked at a lot of different options. Ultimately, we went with creating user backends from the CLI, which is a little bit less user intuitive, but also I think had a very nice separation between the responsibilities of the dashboard, which manipulates the PostgreSQL database and data, and the CLI, which manages all of the AWS resource handling. So in this case, there wasn't really like a clear-cut answer of which direction to go, which made it challenging. And so ultimately, we kind of had to weigh the pros and cons of each, and decided to go with all of the AWS management through the CLI.
Mhm. Definitely. Yeah, because the original vision, we wanted to have it all go through the dashboard. But at a certain point, messing around with credentials and passing them around, that's just not something that we really wanted to do. Yes, it looks like we got another question here. So how did you handle the division of labor? And what did you learn about working as a team that you feel helped things go more smoothly? It's a good question. Yeah, I mean, we can kind of go around the horn with this one, if that's all right with you guys. I feel like we did a lot of things in sort of like two prongs, because we were a team of three. So like whatever was the most necessary at the moment, then we would kind of put two on it. And then the other person would be building out, like sort of like working in parallel. So just to give you an example, like Peter's very organized, so he had some good ideas for the infrastructure from the very beginning, and Show's very good with design. So he had some really good ideas for building out the front end or that dashboard UI. So I was kind of the deckhand, going back and forth a little bit between those two. But then, if we needed more hands in one direction or less hands in the other, and we would just kind of like shifted responsibilities depending on what the, I guess like what the most urgent need was. When there was a time we were having issues, I guess, not issues, but getting everything up and running, like the infrastructure, then all the focus was on that. When there was things that was less urgent or less challenging, then we could kind of divide the responsibilities between those two sides of our project.
Yeah, I can contribute to that as well. So like Jared said, I think in terms of like division of labor, I think it kind of fit nicely in terms of like to what tasks kind of played into certain people's strengths. So Show is very good at design. So in terms of like doing the dashboard, the front end, doing a lot of the graphics, definitely played to his strengths. So ultimately, a lot of times it's like, hey, I'm really interested in doing this. So then that person would kind of tackle that particular area. We did sometimes like collaborate, work three people on one problem sometimes if it was a really challenging thing, like working with AWS. And in terms of like helping or things that helped us to work as a team smoothly, I think that communication is definitely a big part in terms of how we were able to pull this off. Just being able to, talk to each other on Slack every day, and having just, we had 2 team meetings. So one in the morning, kind of like discussing what our plan is for the day, kind of map out our activities for that day. And then a second meeting, like in the middle of the day to kind of recap what we did, what we're gonna do this afternoon, and potentially kind of plan for next week. So I think being in constant communication really helped. And I prefer like over communicating versus under communicating. So if there's any issues or things, that were trolling us, to just kind of, bring it up in an open environment. So I really enjoyed that, having like a very open communication channel with the team.
For sure. Yeah, and I think we all kind of made it a point to develop a relationship early. We were going through prep. We started meeting up a few times a week, and then just throughout Capstone, we were doing those meetups twice a day. And just everybody's always in the loop, always connected. So I think that's a great point, Peter, and it was really helpful. All right. Are there any more questions in the Q&A or either to the chat? We'll give it another minute and then fold it up. Okay. All right, yeah, it looks like that is all the questions for us today. So we just want to thank everybody again for attending our presentation. Again, we're really proud of it, so we're happy to share it with y'all.